welcome back. Today we are going to start with a new topic, that is chemical energetics. In the first part of this series, basically we are going to talk about the introduction to the domain of energetics and then chemical energetics. Thereafter we will relate energetics with thermodynamics and then talk about the significance of thermodynamics in chemistry or in chemical systems. Thereafter, since we are going to focus attention on to thermodynamics thereafter, we will talk about different thermodynamic terms. We will try to define them and tell what exactly do they mean in the context of thermodynamics. Then we will define what is a thermodynamic process and talk about different kind of thermodynamic processes. And towards the end, we will sum up what we do in today's session. Okay, now let's make a beginning by making a statement, that is, energy is at the core of the existence of the universe and all life forms on our planet Earth. Let's make one more statement, that is, their sustenance involves flow and transformation of energy. What does it mean? This means the following, that the existence of this universe and all life forms on our planet Earth, they depend heavily on to energy. Energy is at the core of the existence of universe and different life forms there. Further, their sustenance involves, sustenance means their continuation. That means for the universe to exist and for the life forms to continue to exist, there has to be flow and transformation of energy. That is the basic premise over here. And the study of such a flow and transformation of energy within a given system and between the system and the surroundings is called energetics. So energetics basically is a very broad field, and that broad field encompasses all kind of flows and transformations of energy. That's a very broad term there. And then when we go further down a bit and then talk about the study of flow and transformation of energy within chemical system or between the chemical system and their surroundings, then we talk about what's called as chemical energetics. So energetics is a broad field, but when we essentially it means flow and transformation of energy. But when we try to do that in the context of chemical reactions or chemical systems, that becomes chemical energetics. Further, when we talk about flow and transformation of energy, this energy could be of any type, say as heat, as radiation, work, or any other form for that matter. So all kind of energies, the flow and transformation of them basically means we're talking about chemical energetics. It's important to note that suppose we do a similar kind of a study of flow and transformation of energy in a biological system, then this will be termed as bioenergetics. So energetics is a broader term. So, and then depending on what field do you apply in, it accordingly becomes a new term altogether. Further, actually what happens is, fine, we have defined it chemical energetics to be a study of flow and transformation of energy, and energy could be in any form there. But primarily if you look at in chemistry or in chemical systems, our main concern is flow and transformation of energy as heat. Because our main concern is on how does heat get transferred to the system or from the system, and so on and so forth. And that actually takes us to a little familiar field that is called as thermodynamics. So actually that's a relationship between chemical energetics and thermodynamics. You see now that there are three things we have done so far. One is energetics, a very broad field, very big field, which basically is flow and transformation of energy of any kind, anywhere. Then we've tried to limit it to, bring it to the domain of chemical systems, then it becomes chemical energetics. And then if we further kind of focus down, narrow down to the flow and transformation of heat, that becomes thermodynamics. And that's what you're familiar with. Okay, so since in this course also we're going to talk primarily about flow and transformation of heat, essentially thermodynamics, so we need to get into more details about thermodynamics there. Okay, now what is this thermodynamics? You have learned about thermodynamics in your school also, and you know what it is. Let's try to revisit it. Basically, thermodynamics again is a very broad domain of science, and the basic premise of this of the thermodynamics is there are sort of generalizations of the observations of macroscopic world. Basically what has happened is, over a period of time, a lot of workers, scientific workers, have observed nature, the behavior of nature, and then that behavior of nature has been especially with reference to energy transformations, and that has been documented in terms of what are called as laws of thermodynamics. Now you are familiar with different laws of thermodynamics: law one, first law of thermodynamics, second law of thermodynamics, and third law of thermodynamics, and so on and so forth. Now question comes is that where does this term came up from? This term came up from by this term was coined by Lord Kelvin, and the context there was the dynamic nature of heat, because at that point in time in history, heat was thought to be a fluid, and Kelvin wanted to talk about the movement of heat between the systems and things like that, and just to ensure that it conveys the dynamic nature of it, that means movement of heat, this term was coined as thermodynamics. And if you look closely, thermodynamics actually is a term which is made up of two Greek roots, thermo and dynamikos. Thermo basically refers to heat or temperature, and whereas dynamikos means movement. So literally translated, thermodynamics means movement of heat, dynamism of heat, transfer of heat, and so on and so forth. And that is what exactly we have narrowed down from energetics to chemical energetics to thermodynamics. Okay, now let's see in what way is thermodynamics important for chemistry. Just think it over for yourself. Now, let's see. I'm sure that you have been able to recall, for you, since you have done thermodynamics and you know how have you applied it in the context of chemistry. So let's try to revisit them. The first thing is that it provides us, that's one of the most significant contribution or most significant aspect of thermodynamics in the context of chemistry or chemical reactions, is that it provides us a criterion for determining the feasibility of a reaction. That is very, very important, because we now know that delta G has to be negative for a reaction to be feasible. If the delta G is positive, the reaction is not feasible at all. Okay, that is one bit, and that delta G term, change in free energy, that comes from thermodynamics. Further, it also provides us a criteria and conditions for the equilibrium state for a spontaneous process. We know spontaneous processes, the processes which occur on their own. For such kind of spontaneous process, so what is the criteria for spontaneity, and what are the conditions for equilibrium to be attained in such kind of processes? That also comes from thermodynamics. Third, it also helps us in predicting the direction of a system to attain equilibrium. Suppose the system is not at equilibrium, so we can use thermodynamic understanding to tell which way would the reaction go to attain the equilibrium. And lastly, one more aspect which is important here is that it also provides us information about the extent of reaction in an equilibrium reaction. What does it mean? Now suppose there is an equilibrium reaction having equilibrium, so which way is the equilibrium? Is it towards the reactant side or towards the product side? That also can be ascertained from what's called as equilibrium constant, which again is a thermodynamic quantity. Okay, so a higher magnitude of K will state that the reaction goes more to the forward direction. A lower value of K means reaction goes to more to the left hand side, that is to the reactant side over there. So you see that thermodynamics provides very, very crucial inputs about the chemical reactions in general. Okay, let's move further and now talk about certain terms which we use repeatedly in thermodynamics, and I'm sure that you learned about these before also. Let's try to review them again. The first term happens to be system. System is that part of the universe which is under consideration for the study. That's the way we define it. You can define it any which way. Basically, it means that that whatever part of this whole universe where you are trying to focus attention, which you want to study, that becomes your system. Okay, so let's try to understand with the help of some examples here. The system could be of any kind whatsoever, because there is no restriction of any kind on that. The system could be very small and simple. For example, if I just take a certain amount of water in a beaker and I want to study certain behavior of water taken in a beaker. So that is a system. It's as simple as that. It's very simple and small system there. On the other hand, the thermodynamic system could be very big and complex. I can even talk about the whole ocean. Whole ocean can be taken as a system. Now you see that it is too big, firstly, and secondly also it's very, very complicated. It's very complex because it has so much of constitutions in that. So that means, theoretically speaking, a system is any part of the universe which is under focus for the study, and it could be simple and small or big and complex. Going further, we can see that system may be homogeneous or heterogeneous. What does it mean? I take again two examples here. Suppose I take salt and water. Salt dissolves readily in water and you get a solution of that. So this solution is homogeneous. You take any portion, say I take first sip or the last sip of the salt solution will have the same taste, so to say, or other you can say same concentration. Suppose I take the solution from anywhere in this this beaker here, it will have the same composition. That means same concentration. It is homogeneous. Homogeneous means same throughout. On the other hand, if I take ice and water, this becomes an example of a heterogeneous system. This again is thermodynamic system, but here we can find that there are two phases there. One is a solid phase, one is a liquid phase over there. Okay, let's go ahead and talk about a term what is called as boundary. We are familiar with the term boundary. We use boundary in variety of ways. Boundary of the house, boundary of the colony, or maybe the boundary in a cricket field over there, and so on and so forth. We know what the boundary means there. But now in the context of thermodynamics, boundary has a specific meaning. That is, it is that part which separates the system from its surroundings. That is very, very important. That's the way we define a boundary in the context of thermodynamics. Okay. Now here again, there are different qualifiers for the boundary. Boundary can be real. For example, if I take a test tube, a closed test tube, suppose there are some gases contained in this one. So the gas happens to be my system, and the body of this test tube and the cap on this, that happens to be the boundary. This is separating the contents of the test tube from the surroundings over there. That is a real boundary. We know what exactly is the boundary. We define it very well. On the other hand, the boundary could be imaginary also. Now suppose I take this ozone hole as my system. Then the boundary of ozone hole is not well defined. There is no line in the atmosphere which says, okay, this is ozone hole and this is not ozone hole. That's a very diffuse situation over there. So there is some kind of an imaginary boundary over there. Okay, there's a range where, okay, this is the ozone hole part and this is the outside of that. Okay, so that boundary could be real or imaginary. Going further, boundary could as well be fixed. Suppose I take, again, we could have taken the same example again. Suppose I got a cylinder containing certain amount of gas there, and cylinder is closed from both the ends there. So the boundaries are fixed now. Okay, and another possibility is I have a cylinder, there is a gas content in that, and I have put a massless and frictionless piston on it. By moving the piston up and down, I can change the boundary, and that actually is an example of a movable boundary. So the boundary is something which separates the system and surroundings, and boundary could be real, imaginary, fixed or movable. Okay, I'm sure that you understand what a boundary means in the context of thermodynamics. If we go further and then talk about yet another term which is called as surroundings. Surrounding basically refer to the remaining, that is other than the system part of the universe. Okay, there's a whole universe there, something which you are focusing attention on to, that is the system. Everything else happens to be the surrounding there. And the two put together, system and surrounding put together, make what's called as the universe. That's a third, another term we have to understand here. Let's see it pictorially. So this kind of a irregular circle over there, that is a system there. That's a part I'm trying to focus attention on to. And then this line in greenish color here, that is the boundary. And this system is separated from the surroundings by this boundary over there. And this kind of a squarish picture representation here represents the surroundings. And this whole thing that with this squarish part here, that is the surroundings, boundary and the system, that whole thing constitutes what's called as a universe there. So you actually can't show the universe, but basically it's a schematic representation. That is, this squarish representation is for the universe, and universe has got surrounding, system and the boundary in between them. Okay. Now that is as it goes theoretically, but what is exactly meaning of surroundings in the practical context there? Let's take an example there. There are certain students working in a laboratory here. Now suppose they are doing some experiments, maybe they are doing a titration or making some preparation over there, and so that titration equipment or maybe the preparation equipment, that happens to be the system. Now what is the surrounding? Surrounding could be anything. Suppose they are doing work here in Delhi laboratory, and you are sitting somewhere in Mumbai or Chennai, so your house also is part of the boundary here, part of the surroundings here. Or maybe if you go further, probably an experiment being done in Delhi, the boundaries, even something which is happening in the White House in the US, actually is part of the surroundings there. That is theoretically speaking. But practically what happens is, surroundings can be taken as that part of the surroundings which actually can have influence on the system. There can be some kind of a meaningful interaction between system and the so-called surroundings there. For example, in this case here, now suppose the students are doing a titration here. Okay, so they are doing at a certain room temperature, they are doing it, and suppose there is a burner here, or maybe gas is, there are 2-3 burners which are ignited in the neighborhood over there. So those burners can transmit heat to that system and can influence it. Okay, so that become part of surroundings. Maybe if I go broader, I can take all the people in the lab, could be part of surroundings. Maybe the lab as a whole can be taken as surroundings, but beyond that, no. Because something out of the lab probably will not have any direct or indirect influence onto the system and the study over there. So what I'm basically trying to convey to you is that theoretically speaking, surroundings means everything other than the system. But practically, surroundings means that part of the so-called surroundings which actually can have some kind of a meaningful interaction with the system. They can influence the system directly or indirectly. So that actually happens to be the surrounding. So we have to be clear about, theoretically it could be anything, but practically the surroundings are quite limited. They are in the very, very neighborhood of the system over there. Okay, let's go ahead and talk about that what are different types of systems we have. Because there are a variety of types of systems we can think of, and that actually will depend on what is the nature of the boundary of the system, and also what kind of energy and matter exchanges can take place. The spellings are not correct here. So that actually defines different kind of systems there. Let's take some examples and understand. Now suppose I take, it's a schematic representation here. I take a test tube containing certain amount of, say, water only. Okay, the test tube is open. Now what can happen? I can add more water to this, or maybe I can remove some water from here, or maybe I can warm it with some, say, blower or some kind of a heat there. I can increase the temperature. I can put it into maybe a refrigerator, or maybe I can put the test tube into a ice box and make it get cooled down. That means in such a system, I can have both the possibilities. There can be a matter exchange, that means the contents can be brought in or taken out, or there can be energy exchange. Such a system is called as an open system. Now suppose I take the same test tube and put a lid on this. What happens now? What happens now is, since the test tube is of glass, I can still have energy exchange. I can warm the contents of the glass test tube, and also I can cool them. That means there can be energy exchange, but there is no matter exchange possible there, because of the closed lid over there. I cannot take out water, I can't add more water to this, or water or anything else for that matter. So there is no matter exchange possible now. Such a system in which there is energy exchange, but no matter exchange is called as a closed system. Okay, let's go further and take this test tube and wrap it with some kind of a insulated material over there. Now what happens? Now both the things become impossible now. That means since the test tube is closed one, I can't do any matter exchange. Similarly, since there is insulation there, so I cannot do any energy exchange also. I cannot heat the system, I can't even cool the system because there is insulation over there. Okay, such a system which doesn't allow either the exchange of matter or of energy is called as an isolated system. So there are three kinds of systems over there. Okay, let's look at the same thing in a representation way. What you see is this cube here is a system there, and in this system I have tried to show matter in terms of red arrows and energy in terms of bluish arrows there. So what you find is in the open system, so you can see that the matter can come out of the system, can get into the system. Energy can come out of the system, energy can get into the system. Okay. Whereas in case of closed system, energy can come out and get in, but matter cannot get in, matter cannot come out. Okay. And the third one is an isolated system where neither the energy or the matter can get in or come out of the system. So that is a pictorial representation of thermodynamic systems, three types of that: open, closed and isolated systems there. Okay, let's go ahead and talk about one more term, what is called as a state of a system. Now what exactly we mean by state of a system? If I got a thermodynamic system and I want to communicate about that, suppose I have one thermodynamic system in my lab and I want to talk to you about, I want you to create a similar system over there in your lab at your place, then how do I communicate to you? I must tell, I must give information about different physical properties of the system I'm dealing with. If I'm communicating to you in that form, you can redo that one and create a similar system at your place there. Okay. Basically, when you say state of a system, essentially it is a way of defining the system, and that is done by characterizing or defining a system. And state of a system is defined by specifying the physical properties like pressure, temperature and volume, etc. of the system. If I tell, okay, this is my system, this is the pressure, this is the temperature, this is the volume, then I have defined my system, the state of the system there. So the similar system in the same state can be created anywhere else on the basis of this definition there. And these physical properties which we have to specify to define a state of system are called as thermodynamic properties or thermodynamic variables there. And since they talk about the state of a system, they depend on the state of the system, they are also called as state variables there. We'll talk more about it as we move further up there. So basically, state means a system defined in terms of different physical properties for the same. Okay, let's go ahead and see that the state variables which depend on other variable is called as a dependent variable, because there are a number of state variables there. For a given state of system, a given system can be having a state, and that state can be defined in terms of number of variables there, and between these variables a given variable could be dependent on other variables, and other variables on which this is dependent, they are called as independent variables there. Let's understand with the help of examples there. So the state variable which depends on other variables is called as dependent variable, and the variables on which it is dependent are called as independent variables. The simplest example of this could be taken as, say, suppose I have got a sample of an ideal gas, and we know that for ideal gas system PV is equal to nRT. If I just rearrange that one, I can put V to be equal to nRT by P. Now in this expression we know that R is a constant, you forget about that. Now we see that value of V will depend on the value of N, T and P. That means V is a dependent variable whose value depends on the value of N, T and P, and these N, T, P are the independent variables there. That's the meaning of this statement there. And R actually happens to be a constant, so we don't talk about that. It's not a variable, it's a constant. Okay. Suppose I can put the same expression in a different way. I can put it in, say, P is equal to nRT by V. Now what happens is, now P becomes a dependent variable and N, T and V become independent variables there. So that's the way we have to understand that there is a state of a system, there are state variables there, and the state variables could be dependent or independent there. Okay, let's go further and talk about two different variants, because this is again very important there, two different variants of these variables there. One are called as intensive, second is called as extensive variables. Let's understand what these are. Intensive variables are the ones which are independent of the amount or the mass of the system. For example, now suppose I take a big slab of, say, ice and measure its temperature. It has a certain amount of temperature there. Now I take this ice and crush it into small pieces and take a tiny piece of that and measure temperature. It will be same, because the temperature of ice will not depend on whether it's a small piece of ice or a large chunk of ice or maybe a big slab of ice. The temperature will remain the same. So temperature is a independent, or not independent, it's a intensive variable. It depends, it's independent of the mass or amount of the system over there. The second variety happens to be extensive, just opposite of intensive, which depends on the amount of the substance. Now, for example, if I want to talk about, say, volume, if I take 1 mole of water, 1 mole of water means 18 grams of water. If I take density to be 1, so that becomes 18 centimeter cube of water. That means the volume of 1 mole of water is 18 centimeter cube. If I take the volume of 10 moles of water, it will be 180 centimeter cube. So what you find is that volume depends on the amount. This is 1 mole, amount here is 1 mole, amount here is 10 moles. So since the amount has increased, the volume also has increased. So the volume is a extensive variable that depends on the mass or the amount of the system over there. Similarly, even mass is an extensive variable. Suppose I take, what is the mass of 1 mole of water? 18 gram. Mass of 10 moles of water? 180 grams. Okay, so mass and volume are the examples of extensive variables, whereas temperature is an example of an intensive variable. And one more important thing we have to understand here is, that is, the ratio of two extensive variables is always intensive. Let's take an example again. Say density. Density is defined as mass per unit volume, we know that. Mass we have seen is extensive variable, so is volume. So the ratio happens to be density, and this density is an intensive variable. Let's take the example again. Suppose you take a beaker, there's a certain amount of say water in that. Okay, you measure the density, it has a certain density value. You add more water to that, similar, just increase the volume of that one. Again, it will have the same density. So density will not depend on how much of water have you taken. It will be the same over there. Okay, so that is about the intensive and extensive variables. Let's go further and talk about, when we say a thermodynamic process, what exactly we mean by that. A thermodynamic process basically means that a change in state of the system. That means if I somehow change the state of a given system, I say I have carried out a thermodynamic process. Let's take an example to understand this. Now suppose I have taken a beaker, and the beaker I have taken 150 grams of water, and the temperature happens to be 20 degrees centigrade. And since I have taken it an open beaker, so the pressure will be atmospheric pressure over there. So it is P, 150 grams, 20 degrees centigrade. So essentially I have defined the thermodynamic properties or parameters over there. So I have defined, so these three things define the state of this system. My system is water in beaker. Okay, and in this system, these are the qualifiers for that. So these three parameters define this system there. Now if I somehow heat the water in this beaker and take it to about 50 degrees centigrade, you can see the temperature has increased out there. It was 20 here, it will become 50. So what has happened? Though this is a new state now, because the properties have changed. This has not changed, this has not changed, but this has changed. So this becomes a different state. This was state 1, this is state 2. So when you do so, when you go from a given state of system to another state of system, we say we have done a thermodynamic process. So thermodynamic process basically means change of state of a system. And it's important to note that in a thermodynamic process, it involves changing at least one of the thermodynamic variables. Now suppose I don't change any thermodynamic variable, then there's no process. Suppose I had the say 150 grams of water at 20 degrees centigrade and I don't do anything to that. I leave it as such. The system remains what it is. There's no change, there's no process. Okay, so it's a must that for any process to be there, at least one of the thermodynamic properties must change. That's very important here. Okay, and then sometimes it happens is you can have a thermodynamic process which occurs in number of steps there, such that the system starts from a given state, comes back to same state. Then we say it is called as a cyclic process. Let's take say a system is state A here, and I do some process to this and take it to state B. Then I do one more process and bring it back to state A. So if I see from here, system started from state A is back to state A. So this whole process, the overall process, because in this case it happens to be of 2 steps. So that overall process will be called as a cyclic process, because the system has come back to its original state. But you remember I initially said, if you don't change any parameter, if in this case you can see that effectively there is no change in any parameter because same state has come back. So from an earlier version, there is no thermodynamic process. That may be true if you are looking from outside. But since we have carried out a number of steps over there, I have just taken an example of 2 steps there. You can have n number of steps there. You can have 4, 5, 6, 7 steps, any number of steps. If you come back to that, that will be called as a cyclic process. Okay, let's go ahead and talk about certain important thermodynamic processes. Actually, these are the processes in which one of the parameters is held constant. That's why they are given special names over there. Let's learn about these processes. Now, the first of such process is called as isothermal process. Iso means same, thermal means temperature. That means any process in which the temperature of the system remains constant is called as an isothermal process. How does that happen? Basically what happens is the heat flow into or out of the system occurs so slowly. That means there is a system, there is surrounding, there can be energy exchange between system and surrounding, but that happens so very slow that for all practical purposes the system and surroundings are at the same temperature, they are at thermal equilibrium. So such processes are called as isothermal processes. Okay, and for gaseous systems we know that for an ideal gas we know that PV is equal to constant, and that is constant only at a given temperature, because we know that PV is equal to nRT. We just talked about that. So N, suppose I take 1 mole of a gas, so N becomes 1. R we know is a gas constant, that's again constant, and if we keep T also constant, so then nRT becomes constant, so PV becomes constant here. And in such a case, if I plot a graph between pressure and volume, it will have the following form there. So at any volume or pressure, product will be a constant over there. So this is such kind of diagrams are called as indicator diagrams there. The second process we take is say an adiabatic process. Adiabatic process basically are the ones in which there is no exchange of heat between system and the surroundings there. That means heat can neither get into the system or get out of the system there, and that is possible only when the system has thermal insulation. That means their system is thermally insulated. For example, I do a reaction in a thermos flask, so there is no exchange of heat with the surroundings, between the system and the surroundings over there. So such a system will be, and such a process if you occur in the thermos flask will be an adiabatic process. But one important thing here is that in an adiabatic process, it's always accompanied by a change in the temperature of the system. Let's understand this. Now suppose I take a thermos flask. In that thermos flask, I have taken say certain amount of dilute hydrochloric acid. Fine. And to this I add a dilute solution of say sodium hydroxide and close the lid immediately. What will happen? Now acid and base will neutralize each other, and we know that this reaction is exothermic. Heat will be generated there. Heat is generated there, but it can't go out because we are doing the reaction in a thermos flask. It's insulation there. Since the heat energy cannot come out, so what will happen? Where would that heat go? That heat will go to raise the temperature of the product of the reaction, because we know that acid and base react to give you salt and water. So essentially, if the amounts of the acid and base were equal, what you will be getting is a salt solution, and that salt solution will be at a higher temperature. That means the temperature of system would increase. If you can have, suppose I do a reaction which is endothermic one, which absorbs heat. So in that case, the temperature of system will decrease, because there is no heat exchange possible between system and the surrounding, because of the walls of the system being insulated once there. Okay. And again, this is an indicator diagram for a gaseous system there under adiabatic conditions. We find that in such a situation, PV gamma is equal to constant. We will talk more about it when we get into details of such systems there. But for now, just to see that the slope of this curve is different from what we had in case of isothermal systems. For right now, this is enough. We'll talk more about it when we talk about adiabatic systems in a little later sessions over there. Okay, let's take up the third type of process there. That is isobaric, also called as isopiastic sometimes. Iso is same, baric means pressure, system where the pressure remains constant. So there is no change in the pressure of the system, and the examples could be, suppose I take water in a beaker and start heating it. So pressure doesn't change, pressure is atmospheric pressure. The vapor pressure of the system might change, but the pressure on the system does not change. So such a process is an example of an isobaric process. Similarly, for gaseous system, you can represent the relationship between P and V to be under isobaric condition. When the pressure remains constant, the volume will change, and this is the kind of curve we will get for such a system there. And lastly, another process we take up is isochoric. These are the ones wherein the volume doesn't change. And in such a case, example could be combustion of substance in a bomb calorimeter. This again you will be learning when you talk about thermochemistry. I'm sure that you learned about thermochemistry in your school also. You may be familiar with what's a bomb calorimeter, but for now we will not discuss about it. We'll talk about it when we talk about thermochemistry at a later stage. And again, just for the sake of it, for a gaseous system, an isochoric process can be represented by the following indicator diagram over there. So you can see that here the volume remains the same, pressure is changing, volume doesn't change. It's an isochoric process there. Okay, now let's sum up what we've done today. What basically we've done is, we started by defining what is energetics, then bringing it down to the context of chemical energetics, wherein we said we talk about the flow and transformation of energy of any kind. Then we came down to thermodynamics, where we talked about, that is, the flow and transformation of heat as a form of energy there. And therein we introduced the relationship between energetics and thermodynamics, and then we outlined the significance of thermodynamics in chemical systems, where we talked about delta G, K and things like that over there. Having done that, we took up different thermodynamic terms there, different terms which define thermodynamic systems there, that is like system, surrounding, universe, boundary, and so on and so forth. What is the state of a system, what are the state variables, and so on and so forth. We defined all these terms and also explained what do they mean to us. And thereafter, we defined what is a thermodynamic process. We defined a process to be any change in state of the system. Then we took up different types of thermodynamic processes over there. So for today, that is all what I want to talk about. In the next session, we will talk about heat, work and heat capacity. Thank you very much.